Welcome to video 14 in my rotational motion playlist. Today we'll solve a great problem using the moment of inertia tensor. This problem discusses the precession of a book as it moves through space. In the first example, there is no precession. The book spins smoothly in a single plane without any wobbling or tumbling. This is a simple stable rotation around one axis. In the second example, I apply rotation in more than one direction before releasing the book. As it travels through the air, it begins to tumble and rotate across multiple axes. This is known as precession. I'll read the problem now. A square plate of side length L and mass m is tossed into the air, spinning freely with no external torques. Its rotational period is 1 second, and the rotation axis, in the direction of this vector omega, makes a 45-degree angle with the z-axis. What is the precession period of the book? And question 2 is a conceptual question. What's the difference between the precession period and the wobble period of a rotating body? This slide helps visualize precession, rotation, and wobble. We'll explore these concepts more thoroughly as we work through the equations. On the right is a spinning top. This arrow represents rotation. The top is spinning about its symmetry axis. Precession is when the rotation axis moves in this cone about the fixed angular momentum, which is aligned with the z-axis. On the left, wobble is also shown. Wobble is small periodic oscillations in the direction of omega as it precesses around L. This picture is a little misleading. There's wobble on one side and no wobble on the other. I was just showing the difference, but in reality, if wobble existed, it would go all the way around the entire circle, not just for part of it. Let's talk about Euler's equations. This equation tells us how angular momentum changes with time. That's also known as torque. On the left side, we have the derivative of angular momentum with respect to time in the inertial frame. That's this fixed coordinate system, x, y, z. But in many problems, it's easier to work in the body fixed rotating frame, one that spins with the object. That's the prime coordinate system. As this block rotates through space, the orientation of the prime coordinate system relative to the block remains the same. The point is, it makes the math easier if we rewrite the equations in terms of what an observer inside the rotating frame would see. First, you measure the angular momentum changing within the frame. But second, because the rotating frame itself changes directions, we need a correction term. This is omega cross L. It accounts for the frame's rotation. In the rotating frame, the inertia tensor becomes diagonal. This makes the math much simpler, which is why we like to use this frame. This is a pivotal equation, but also a confusing one. It's the kind you need to sit with, think through, and explain to yourself. Real understanding often comes only when you work it out on your own. Starting with this equation, we're going to derive Euler's equations. We're going to be working in the rotating reference frame, because in that frame, the moment of inertia tensor is diagonal. First, we need this term. Angular momentum L is equal to I times omega. Omega, the angular velocity vector, has three components: omega 1 or omega x, omega 2 or omega y, omega 3 or omega z. L equals I times omega, and that's simply this vector because the moment of inertia tensor is diagonal. That's the whole point. And therefore, this is dl dt, the first term. As the object moves, the principal moments of inertia remain constant in the rotating body frame. However, the angular velocity components can change. That's why you see the time derivative there. Now we can work out this term, omega cross L. This is the omega vector, this is the L vector, this is the standard cross product. I can replace the components of L with their moment of inertia and omega values. For example, L3 equals I3 omega 3, L2 equals I2 omega 2, and we have this expression. Combining these two, we get the Euler equations, which are in this box. These equations are essential for understanding rotation, spinning tops, satellites, and rotating plates. And yeah, they are confusing. Now I will use the three Euler equations to solve for the precession frequency of the book when it's thrown into the air. When the book is thrown into the air, there's no external torque. So torque 1, torque 2, and torque 3 are all equal to 0. This is equation 1. I set it equal to 0. I can rearrange this and do some simple algebra, get this expression for the time derivative of omega 1. This tells how the x component of angular velocity is changing. I3 is Iz. Both I1 and I2 are I because the plate is symmetric. This is the second Euler equation. I can set it equal to 0, do the same manipulation, and solve for the time derivative of omega 2. That's equal to omega 3, omega 1 times Iz minus I over I. Then I can take the derivative of omega 2. That's equal to this expression, which has an omega 1 dot in it. I can then replace omega 1 dot with the right side of the equal sign. We're left with this differential equation for how omega 2 behaves with time. This is the equation of a simple harmonic oscillator. This is an expression for the precession frequency. That's related to how quickly omega moves around this circle. This is the precession frequency that the problem was asking us to find. We know all of the information. We were given the period of rotation as 1 second. Omega is 2 pi over t. When you replace t with 1, you get 2 pi. Alpha is equal to 45 degrees. For a plate, LZ is equal to 2i, so 2i minus I over I is just 1. The square root expression is equal to 1, and we find that the period of precession is equal to the square root of 2 seconds.
Let's talk about the difference between precession and wobble frequency. Precession, also called free precession when there's no external torque, is when the angular velocity vector, omega, slowly moves around a fixed direction, usually the direction of the angular momentum vector, L. This happens when the object is spinning about an axis that is not a principal axis. Wobble, also known as nutation, is a small oscillation that's superimposed on top of the precession. It looks like little ripples or bobbing motions along the precession path.
AcePhysics.org. Math and Physics Tutoring with Dr. H.
Let's go.
AcePhysics.org. Math and Physics
Just
Tutoring.
wow. This is a
Dr.
dream come
Hudis.
true.